somewhat, but there's no help because the group is very large and I have to split you up. But today we will wind up with limits, and that means that first of all, from the last lecture, from the previous lecture, we still have to do some comparison of infinitesimals to finish, and then we will move on to continuous functions, how to use limits, what is the role of limits for functions actually, and then whatever time remains, we will dedicate to a little bit of more practice for limits. And so, comparison of infinitesimals. Just let me switch off the camera. Okay, there we go.
Ma'am.
Yes, what?
Hi, you haven't uploaded the mark list, yeah, for last retake of unit test 3 and the midterm examination.
I haven't put in the retake marks for the third test, not for the third test yet, and not for the midterm. I have to do things gradually because I have many things to do. So I finish one thing up and I put in. So I have updated all the elementary mathematics marks and I have updated all the second test marks. The third test retakes still have to be updated. And so the equivalence of infinitesimals, there was this idea of two infinitesimals are considered equivalent if their limit if the limit of the ratio is 1. So basically what we meant by that was if the limit of two infinitesimals, alpha and, for example, beta, as x tends to any specific value is 1, we call these infinitesimals equivalent. This is alpha and this is beta. It's not a b. If the ratio has limit 1. It means that as x tends to that special value x0, these infinitesimals are not only both approaching 0, but they are also so similar, so very similar, that they basically are the same for very small for very small values of these infinitesimals as x approaches whatever it approaches. And of course, the most standard, the most classical limits are, of course, when x tends to 0. And when x tends to 0, last time we already saw, there were 4 and 4 more. In fact, 8 very special equivalences. And those were sine x, tangent x, arc sine x, arc tangent x are all equivalent to x because we already know that the limits of these ratios were equal to 1. And then there were some more. Exponential e to power x minus 1 is equivalent to x. Natural logarithm of 1 plus x is equivalent to x when x tends to 0. So for very small x values, of course, when x is 0, then natural logarithm is 0 and x is 0, so the limit, the quotient doesn't exist. But even when they approach 0, when x approaches 0, not is, but approaches, the ratio actually tends to 1. These functions tend to be very similar by values. In the same way, trigonometric difference 1 minus cosine x, and remember we used this in many limits, actually is equivalent to x squared divided by 2. And finally, 1 plus x to any power alpha minus 1 is equivalent to alpha times x. That is, if we have 1 plus x squared minus 1, it's equivalent to 2x. If we have 1 plus x to the power, let's say, minus 1, that is 1 divided by 1 plus x, that would be, and minus 1, that would be equivalent to minus 1 times x. If we have the square root of 1 plus x, so that was a very special thing, a very special case. If I had square root of 1 plus x and then minus 1. It is equivalent to 1/2 x because the square root in this case means exponent 1/2. And this is very useful because this way, if you remember and if you know how to use this equivalence, it actually makes estimating some limits, evaluating some limits, very, very easy. In fact, easier than using L'Hopital's rule. And while we are on this topic, I have also published your homework and I also marked it there. No L'Hopital's rule for this unit. The same applies for the test. L'Hopital's rule is not accepted for this particular unit. Next unit, end of next unit, yes. But for now, we are focusing on the classical methods. That would be classical methods of transforming the expressions for the limits and also for using equivalences. And now let's have a look at some examples of how to use these equivalences. The first example, limit of natural logarithm of 1 plus 2x divided by sine of 3x. Now let's remember some of those equivalences. X tends to 0, so we can use the previous information. Now notice ln of 1 plus x is equivalent to x, which means in this case I can think, the way I think will be ln of 1 plus t is equivalent to t, of course, as t tends to 0, which means using these equivalences as x tends to 0, ln of 1 plus 2x is equivalent to 2x. And in the ratio, I may substitute. It is allowed, it's perfectly normal to substitute 2x for ln of 1 plus 2x. And sine of 3x, we already know similarly, sine of t is equivalent to t, so sine of 3x will be equivalent to 3x. We substitute by using equivalences. In the situation of test, it would be actually good to note using equivalence. Using equivalence, or if you like, you can write on the side, actually it is quite possible to write ln of 1 plus 2x is equivalent to 2x, sine of 3x is equivalent to 3x, and then go on to writing this. It's also possible. So some commentary should be done if you are doing this using this equivalence. And so we have, of course, we can cancel out x, and the value of this limit is just 2/3. Very, very easy to find. Very, very easy to find this one. I want to return back to this. In the limit of a ratio of 2 infinitesimals, not in any other situation. That's important. You cannot just go on plopping in the equivalent infinitesimals anywhere, only if it's the limit of a ratio. So only if it's a quotient of 2 infinitesimals. Only then you can substitute one, or if you like both, by equivalent infinitesimals. Only the limit of a ratio. So in this case, yes, we have a ratio, ln divided by sine, so it's a quotient. In this case, it's perfectly legitimate. We can do this. Next example, again the same thing. I am again reminding you that ln of 1 plus t is equivalent to t, or you can write it like this. You can even write this. So this means, and of course, when x tends to 0, we know that x and sine x both tend to 0. These two things both tend to 0. So ln of 1 plus 0, of course, tends to 0. So it is 0 over 0. It will be the ratio of 2 infinitesimals. It is indeed the ratio of 2 infinitesimals. Perhaps I should better write it like this. It is 0 over 0, and I'm putting it in quadratic in square brackets. So now I'm writing down ln of 1 plus t is equivalent to t, and now I can write limit when x tends to 0 of, instead of 1 plus ln of 1 plus t, I write t. This is t. This is t. So I write 2x sine x divided by, and now I know that tangent of t is equivalent to t, so I actually write x squared, which is t in this case. This is t. So now we can very, very easily cancel out x. So we have 2 lim sine x divided by x when x tends to 0. This is a standard limit. No need to substitute anything at all. This is the standard limit. This is 1. So it's 2 times 1, actually equal to 2. It's not plus, it's not minus, it's times. It's times. So in principle, this, as you see, using equivalence of infinitesimals really makes things easy. Really makes things easy. If you can keep those infinitesimals in front of you during the rest, actually the formulae are always on screen during their unit test. And those people who ignore those and are grabbing for something else are not very clever, I have to say. Because the formulae are always during the test, they are always on the screen, the most important things. And in the limit test, these will be on the screen. These formula will be on the screen. The test actually will consist of some limits and a function to investigate using limits. Not much, but basically 9 limits and a function, or 8 limits and a function, something like that. Case C, very simple again. In this case, we know that e to power t as an infinitesimal minus 1 is equivalent to t. T in this case is 3x. Again, very easy and very simple, the simplest thing that can happen. So 3x over x, and the limit is 3, of course. So this is basically a simple case, a simple thing that happens. Now let's go on with the next. This is what I meant by alpha. Now let's see. 1 plus t to power 1/2, square root is power 1/2 minus 1, is equivalent to 1/2 t. This is something I wrote on the board already a while ago. So in this case, let's note, well, I take it for granted that you do know that the square root means exponent 1/2. So this will be limit when x tends to 0 of, evidently, instead of t, we have 2x. So this is t, this is t in one case, and this will be t in the other case, as you can see. So I'm going back to, it is 1/2, that's alpha, times t, which is 2x. All right. Why do I have this? Just a moment. I need to erase one thing. Eraser, erase this. Let's go back. Now, tangent, of course, as always, tangent of t is equivalent to t, so we can write 5x. So what we see is limit. Okay, I will still write x tends to 0 of x over 5x. Now I know that x and x can be cancelled out, so we have 1/5 for this limit. So infinitesimals, I can promise you that in the limit test next time, you will have examples where using infinitesimals, using this equivalence, is actually very, very useful and something that you should be doing, because that, as you see, gives you a very simple approach. Now, this limit is something you can do in 2 different ways. You can do it using infinitesimals, or you can do it using the trigonometric limit. That's your choice. That's your choice. So if we use trigonometric limit, I would say, okay, I have to multiply by 1 plus cosine 2x, which means I need to multiply this by 1 plus cosine 2x not to lose the value. Also, I noticed that many of you still do not use appropriate parentheses. You lose points for not using parentheses, as is appropriate in mathematics. You are very sloppy in that aspect. Now, let's take care of this. So we have 1 plus cosine x, 1 plus cosine x. So remember that this was 1 minus cosine square of 2x. That is, it is actually sine square of 2x. When x tends to 0 times 1 plus cosine x. And here we have these two together. That is 1 minus cosine square. That is sine square of x times 1 plus cosine 2x was remaining there. So these two, this tends to 2, remember, this tends to 2 because cosine tends to 1. So these will basically disappear, and then we will be able to go on with the trigonometric approach. However, if we use the same limit, and now I will show you the same limit using the equivalence approach. So it was originally 1 minus cosine 2x divided by 1, minus, uh, 1 minus cosine x. Now remember that 1 minus cosine t is equivalent to t squared divided by 2. So I have to think 2x is t squared divided by 2, and here we have simply x squared divided by 2. Now I will multiply by 2, multiply by 2, multiply by 2. Let's put it this way so that we can cancel these things out. I will change the color a little bit. So I can cancel out these two things. It makes it a bit easier to consider. So multiply the denominator and numerator by 2. And now we have, I won't change the color anymore, 4x squared, don't forget to square the 2, divided by x squared, so very obviously it's 4. This limit is 4. Slightly surprising perhaps, but, or perhaps not so. Not so much. If we worked with these limits using trigonometry, remember you would need to divide by 2x squared and multiply by 2x squared, and in the end you would still get the same situation. After you simplify things, after you simplify the limits, you would still get the same thing in the end. But as you can see, much less writing, much easier to do is the equivalence approach. But it's up to you which method you use. In many cases, you can use the standard method because in many cases, infinitesimals cannot be used. And then there will be situations where only infinitesimals will help. And then there will be situations like this where you can choose. Now, the next part of today's lesson, continuous functions. And what remains, well, for the remaining time, practice exercises. In your lecture transcripts, this corresponds to 4.5, 4.6, or was it 5a for practice? Let's have a look at continuous functions. What does it mean, a continuous function? Well, evidently, a function that is continuous doesn't have any gaps. This is where the one-sided limits come in. So what does it mean? A function is continuous. It means that the function from the limit's viewpoint, this is from the limit's viewpoint, the function is defined at x equals a, So in principle, I might think something like this. We have a function. We have a, so first of all, the function is defined, the value exists, it's not really a gap. There is a value at this x value. At the moment, I simply have not drawn it yet. Next, a limit, a finite limit exists. This means when we approach x from both sides, both one-sided limits are the same, both one-sided limits are exactly the same. This means, indeed, both one-sided limits being the same. If a limit exists, finite, means a value, a number. It doesn't go off to infinity. And finally, the limit is actually equal to the function value. So this means that the function from both sides actually tends to the value it indeed has. Was that a question or was that simply an accident? I guess an accident. Okay. So what happens? What does this mean? Function is defined, so a value exists, a limit exists on both sides, and the third point is they are both the same. The function value and the limit actually coincide. F of a, that is this function value, So this means that function has a value. It's not simply a hole in the graph. Next, the limit exists. That means both one-sided limits go to the same point. From both sides, the function approaches the same as you can see. And in fact, it is also the function value. So these three conditions, these are both very important. A finite limit exists. It means the function value is not only a one-sided limit. Function is defined, and yes, the function value is exactly that. So what that means colloquially in normal understanding is that I can sketch this graph. And I will take, let's say, a different color. I can sketch this graph without taking pen off the paper or board or screen. So I can simply sketch this graph without anything. So a discontinuous function, a function that is not continuous, would mean that I have to interrupt my curve. Maybe it has a hole, maybe it actually goes to infinity, but that would still mean I have to interrupt. So it is continuous on an interval if it's continuous at all points. So basically, we could say that function is continuous at So what are the? I'll go back so that you can write down things. Those of you who do. So to think of discontinuous points, this simply means that there might be an interval of x where the function is continuous, then there's a disruption, and then the function is continuous for another interval, and then there may be the function is continuous on another interval, even if it goes to infinity. So you see, these would be intervals where the function is continuous. On this interval, on this interval, on this interval, the function is continuous. Basically, the points where the function is not continuous separate such intervals. But there will be intervals where the function is continuous. In principle, if you remember back, this means we can consider these compound functions, the functions that were defined on segments, the functions that were actually described by perhaps different formulae on different segments, the compound functions. We will have examples a little bit later in a few minutes. Now I'm going on to discontinuity, types of discontinuity. When can a function be discontinuous? that is not continuous. Type 1, both one-sided limits exist. One-sided limits exist and are finite. That means nothing goes to infinity. Nothing goes up or down. They are finite. Both limits exist. The problem is evidently something with these one-sided limits. So the first case, the one-sided limits exist, they are finite, but they are not the same. Something like this. You don't have to mark this delta x, you don't have to mark this, but just notice this particular thing from the graph. What does matter? So the picture is actually more complicated because I copied it from a book. I scanned it from a book. But what this means is, on one side, the limit when x tends to a from the left is one number, and at the same time from the other side the limit tends to, when x tends to a, is another number. So you see there's this gap. Really, there's this gap. A leap or a jump, as you see. On one side, we move on to a. The function value tends to one specific value. On the other side, as we approach a, we see the function tends to completely something else. So the two one-sided limits, they do exist, but they are not the same. And naturally, we call it the jump discontinuity, because the function, as you say, it jumps. It simply jumps, and that's it. So this is type 1. Type 1 involves finite values, finite one-sided limits. Finite one-sided limits. Another kind of type 1, still type 1, it's still type 1. So again, still the same. It's still the same.
Excuse me, miss.
Yes.
Can you show previous page for a minute? Thank you.
Okay, don't copy the white picture. Don't copy the white picture because these deltas are not important at this moment. There is an explanation, but I'm not going into those details. I would prefer that you are able to see the graph and understand what's happening. What is happening here is a jump discontinuity. On one side, the limit is some number. On the other side, that one-sided limit is some other number. They are not the same. So there's really a jump. Can I go on to the next one?
Yes, madam, thank you.
Okay, so it's still the same. So you don't have to copy this because it's still the same. It's simply the second case. B. Case B is that these limits are equal. In this case, these limits are equal. Unlike the previous case, in A, the limits were different, distinct. But these two limits are the same. However, the function value is not it. What this means is, it looks something like this. Maybe the function is simply not defined there. It could be simply a hole in the graph, an empty point. But it also could be that there exists a value. It's just something completely different. So what is possible is that we might have this empty dot, empty point. So when x tends to a, from one side, from the other side, yes, the one-sided limits are exactly the same. The function value approaches a specific point, but the actual function value, perhaps the function is not defined. It's possible. Or perhaps somebody has come and said, okay, the function value, let's say the function value at A is a very special moment, and let's define it somewhere else as something else. That is possible. It sometimes can happen. So you might have a complete hole, as in the first picture, let's make it red. You might have a complete hole in there. The value of the limit, in this case, or the function limit is a. In this case, I could say the limit of the function when x tends to x0, in this case, not a. x0 is the value a because both one-sided limits are it. Both one-sided limits are it. However, the function value f of x0 in this case is not equal to a. Maybe it's not defined as in this case. In this case, it's not defined. But in the second case, maybe somebody has come and said, okay, let the function value at this point be something I need. I want, for this one special case, I need the function value to be this. It might happen, for example, for programming, for instance, if you need for some special case to mark some special values of a function as different from others. In real life situation, that might also happen depending on the formula of the function. So that's very special case. That would be very complicated function, however possible. However, it would be possible. So we call this removable discontinuity. Why? Because all we need to say is, okay, so let's define the function value as a at that point. So it's kind of removable. It doesn't mean it makes no sense, but it simply means that it is very easy to define the function value at that point as the limit. We can sort of take the point and plug the hole. We can plug the hole. So even if the point is defined somewhere else, we can redefine. We can simply state, let the function value be that. Again, depends on the situation. Why would we need this? So sometimes it's necessary, sometimes the hypothetical possibility is what matters. It doesn't mean we need to remove it. What is important that it's at least theoretically it's possible to say, let us define the function so that at this particular point the function value is indeed equal to that limit, because this refers to just one point. Just one point can be corrected. We can say, okay, let's do it this way. Not that we always do, but in principle. So these two, type 1, both type 1 discontinuities involve one finite, not one, but they involve finite values of the function. The limits are finite, one-sided limits. Both exist, but they are finite. That's why it's type 1. It does not involve infinity. Type 1 does not involve infinity. And then there is this type 2. This is where one or both one-sided limits are infinite. This type of discontinuity, well, happens for some functions quite naturally. For example, when we have the inverse variation or inverse proportion, for instance, it would look like this. So one-sided limits, one or both. In this case, you see that the left-hand side limit from the left is positive infinity, and limit from the right is negative infinity. So in this case, they are different infinities. They could be both the same, both positive, both negative. It might also happen that just one of the both one-sided limits is infinity, and the other is finite. It's also possible, and we might just be able to see one of those examples today. So this or this. There's no specific name, there's no jump or removable or anything. This is simply type 2 because one or both one-sided limits are infinity. Could be positive infinity, could be negative infinity, could be from the right-hand side, could be from the left-hand side, or both, But in principle, this works like this. Whenever there's infinity involved, it's type 2. It's type 2. So yes, in this case, you might copy this diagram, this picture, or maybe, okay, some other examples. We could say that, for example, function f is 1 over x squared. What this means is that, of course, as x approaches 0, the function value approaches positive infinity. And when x tends to infinity, the function value tends to 0, for instance. This is also the same thing. X is 0 is type 2 discontinuity. It's type 2. This is type 2. Because both one-sided limits go to positive infinity. All right. Now, some examples for this type 1, type 2. And now let's do some examples, some exercises for this. So, type of discontinuity. For that, we need to sketch. We need to understand this function. Now, let's remember x modulus, x absolute value. First of all, let's remember x absolute value is x if x is greater than or equal to 0, and it's minus x if x is negative. We know that. That's about absolute value completely. This is completely about absolute value. So what this means is that if x is greater than or equal to 0, then x absolute value is x. X divided by x is 1. If x is greater than 0, greater than 0, not equal. Why not equal? Because if x is equal to 0, this function is not defined. This function is not defined because 0 divided by 0 could be anything at all. And if x is less than 0, then this absolute value is actually minus x. So minus x divided by x is negative 1. And when x is 0, the function is not defined. So I can write not defined if x is 0. And what the graph would look like, I don't remember if I had, no, I don't have the axes drawn. All right, I have to draw them myself. So now see what happens. Here. If x is greater than 0, then the function value is 1. It's a constant horizontal line. If x is less than 0, the function value is minus 1. Or again, a horizontal line. Okay, I missed this. That was not. Okay, I will draw the correct one. Okay, and then I will be able to erase the other one. Okay. And so what happens when x is 0? Nothing. So this is, as you see very clearly, this is the jump discontinuity. So this is type 1, and this is jump discontinuity. And in this case, the function value at 0 is even. So at x is 0. Type 1, jump discontinuity. So similar situation in the unit test. You have to write down which point, which type, and then if it's type 1, then you also have to note whether it's jump or removable. So we see that we have one point of discontinuity, and it is at x is 0, and it's type 1 jump discontinuity. Because you see the jump here, and also It does not have to be noted, but, well, yes, we know that the function is not defined when x is 0. So really, there's no even separate dot anywhere on this vertical axis. However, sometimes people want to be very clever and say, let's define the function at 0 as whatever we like. But we won't do that. Next function, next graph. So we see that basically this function is not defined. The function is not defined. Let's notice the domain of the function. The domain of this function, x squared minus 1 cannot be equal to 0. So this means x squared cannot be equal to 1. This means x is not positive, negative 1. So we have evidently two points of discontinuity. Perhaps there's more, but as soon as we understand what this graph might look like, we can decide. So 1 divided by x squared minus 1. We understand that at these 2 points, where x is 1 and where x is minus 1, we get 1 divided by 0. So limit when x tends to 1 plus 0 from the positive side, x squared minus 1. X is a bit greater than 0, so this denominator is a bit greater than, x is a bit greater than 1. The denominator is a little bit greater than 0, and that means we have 1 divided by positive 0. 1 divided by positive 0. So this is plus infinity. This is plus infinity. When we have limit x tends to 1 minus 0 from the left, I haven't written anything, I haven't sketched anything yet. So x tends to 1, but it's slightly less. So x squared is slightly less than 1. And so this means that slightly less than 1 minus 1 is slightly less than 0. So it's negative 0. Again, I'm putting it into quotes because this is not exactly, well, it's not division by 0. It's division by something infinitesimal but negative. 1 divided by negative 0 will be negative infinity. So we can perhaps not sketch the whole graph, but at least we understand what's happening when x approaches 1. We understand that when x approaches 1 from the right-hand side, the function value tends to plus infinity and then does something. Then it does something. I'm not interested in what exactly it does. However, we can understand that when x tends to positive infinity, the function value should tend to 0. So in principle, yes, we can sketch something like this. And then I need to erase this part. We can understand the function, the behavior of this function. If x tends to infinity, we can understand that this will tend to 0. All right. So if x tends to 1 from the left, like this, we see the function value tends to negative infinity. Okay, it goes down, down, down there, to negative infinity, and this up here to positive infinity, as you can see. All right, something like that. Again, we don't exactly know how the function behaves clearly because we have not investigated it in more detail, which we will be able to do in some weeks. And now let's think about minus 1. What happens with minus 1? First of all, please note that this function is even. This is an even function because if I replace x by minus x, the function value remains the same. X squared is the same, which means there's a symmetry. The graph is symmetrical about the y-axis, which means for the sake of symmetry, I understand that here from the inside, it still tends to minus infinity, and from the outside it would still tend to plus infinity because the function is even. The graph should be symmetrical. I don't know exactly what happens here, therefore I am not drawing anything there. We are just sketching enough to understand how the limits work. So we can see these are both. So if x is positive or negative 1, then we have type 2 discontinuity. We have type 2 discontinuity at both points because infinity is involved in both cases. So I investigated the positive 1 x value, what happens around positive x 1. From the right hand side, x squared is a little bit greater than 1. From the left hand side, x squared is a little bit less than 1. Hence, the 1 divided by positive 0 or by negative 0. But when x tends to negative 1, from the inside, that is, from the positive direction, x squared is a little bit less than 1. So now we have the symmetrical case because this is an even function. So when we have to sketch this kind of function, then in principle, if we don't know exactly what the graph looks like, it's important that we sketch close to the points of discontinuity, at the dangerous points, at the special points, and the rest is something we guess. The rest is something that we can guess. But the important thing is to understand the behavior of the function close to these points, the points of discontinuity. Next one, I think. Yes, this. All right. What happens here? For almost all x values, y equals x half. X half is a linear function. The slope is 1/2, or we can write y is 1/2 x. The slope is 1/2, which means run 2, rise 1. Run 2, rise 1. So 1, 2, 1. And if x is 0, then y is 0. And that's enough. That's enough. We can sketch this graph. But if x is 2, then the function value is 0. For all x that is not equal to 2, we have the points of this line. At this point, this is empty here. We take it out, as we see, and the function value is 0 at this particular point. So at x is 2, we have type 1, and this will be removable because we created it artificially. We just created this discontinuity artificially. So if I could only cross out this, if I cross out this part, then I can remove this discontinuity. I can plug the hole. But as it is, this is specific artificial definition for this function. In principle, it's linear function, it's a straight line. And yes, we could take this point because it's only used to sketch the line. And then we say, okay, for all points except this, all right, let's remove this. Let's remove this. That's a hole on the line. All points of the line except that one. And at that point, when x is 0, the function is defined separately, differently. So removable discontinuity. A simple case, a simple example. Another one. All right, this is 1. F of x is 1 divided by 1 plus 2 to power 1 over x. 1 divided by 1 plus 2 to the power 1 over x. If you write by hand, it's more understandable like this. So we see what is dangerous. First of all, 2 to any power is positive, which means the whole denominator is never equal to 0. So I can say 1 plus 2 to power whatever is never equal to 0, so we don't have to worry about this. It actually is always positive. It actually is always positive, so the function values are actually always positive where it exists. 1 divided by positive, so that's something preliminary, just to understand that this denominator doesn't hurt anything. So what does hurt anything? 1 divided by x, evidently. You cannot divide by x. However, x cannot be equal to 0. The domain of the function is x is not equal to 0, because here we cannot divide. This quotient actually does not exist, is not defined, or it's infinity actually when x is 0. And now we need to investigate the one-sided limits. So, all right, when x tends to 0 plus 0 from the right, then 1 over x tends to positive infinity. 1 divided by positive infinitesimal means 1 over x tends to positive infinity. Then 2 to power 1 over x. 2 to power positive infinity, imagine, also tends to positive infinity. So this means 1 divided by 1 plus 2 to power 1 over x. 1 divided by infinity is 0. Okay, that's something we already know. So when x tends to 0, this function f of x evidently, strangely enough, also tends to 0. See, x tends to 0, 1 over x, therefore tends to positive infinity. 2 power 1 over x also tends to positive infinity. Now 1 divided by positive infinity tends to positive 0, which means, okay, it's something like this. The graph behaves like this. Interestingly, the function tends to 0, but when x is 0, we cannot say that the function is 0 because the function is actually not defined. You cannot divide by 0 really at that point. Now, the second part, let's consider the second. When x tends to 0 minus 0, so to 0 from the left. Let me remind you that the function is always positive. The function is always positive because powers of 2 are always positive. That's how I knew that it must approach from above. That's how I know that's coming from the positive part, not from the negative part. Now, instead of writing one-sided limits in a complicated way, you see I didn't use the limit notation. To make things simpler for you and for all of us, I did not use the one-sided limit notation, but what I did, okay, 2 people showed up and then they disappeared again. When I write x tends to 0 plus 0, it means I am considering the right-hand side limit, and when x tends to 0 from minus 0, I consider the left-hand side limit. So this means that 1 over x now, so if x tends to 0 staying negative, it means 1 divided by infinitely small is infinitely large but negative, because now x is infinitesimal but negative. Because this is positive, this means here this is negative. 2 to power 1 over x is 2 to power minus infinity. And we know that exponential function, the classical traditional exponential function, 2 to power whatever, when exponent tends to minus infinity, this tends to 0. So I will write tends to 0, approaches 0. And then 1 divided by 1 plus this is 1 divided by 1 plus 0 tends to 1. So actually tends, not is equal to. So when x approaches 0 from the left, the function value tends to 1, strangely enough. So once more, x tends to 0 but is negative. So 1 divided by x is infinity but negative. So 2 to power 1 over x is 2 to power negative infinity, that is, tends to 0. Then if I replace this part by 0, 1 divided by 1 plus 0 is 1. So again, the function is not defined. I cannot put 0 instead of x, but it tends to 1 to this point from the left-hand side. I have no real idea whether the function is increasing or decreasing. Let's have a look. As x gets a greater absolute value, then this gets smaller absolute value, but it's negative. It becomes greater, so it becomes less. Okay, I have no idea. Really, I'm not investigating it. It could be from above, it could be from below. That would mean more serious investigation, but we understand that from the left-hand side, the function value, the limit is 1. The other one-sided limit is 0. So now I can write them down as limits. Limit when x tends to 0 from right of this function is 0. And the one-sided limit when x tends to 0 from the left of the function is 1. So evidently this is, so at x is 0, we have type 1, and this is jump, discontinuity. And you see, we can have a single formula. We don't have to have a compound function even. We have a single formula. We have a single formula for the function, and it still has this jump. And it still has this jump. So jump discontinuity happens. So this was let's say something that was helping us to figure things out. This middle part of the screen is actually where we did figure things out, and the right hand side is where we sketched. So this is the main part for thinking, the main part for figuring things out, for understanding the limits. And then this is the second part where we actually sketch and see how the function works, what the graph looks like. All right, now I'm moving on to practice. So some practice. For practicing limits, a very quick overview. We have half an hour to practice limits. That's very good. A little overview, first of all. And that will be the types of limits. So we can have, let's remember where we started. We started with limits that had indeterminate form 0 over 0. One thing before I go to this, remember that sine is because you can use direct and simply take the situations with radicals here for this. We could have situations with radicals. So for 0 over 0, remember what we did? I hope you do. We multiplied and divided by the conjugate sum. We multiplied and divided by the conjugate sum. But if we had infinity over infinity with radicals, what we did was, no, there's no need for conjugate sum. We still divide out highest power. Still the same. So you see this conjugate sum is only used for 0 over 0. You have to pay careful attention because otherwise you do a lot of unnecessary extra work. If you try to use conjugate sum for this, it's mostly useless. Mostly useless because you will, in the end, you will still need to divide out the highest power of infinity. So in this case, don't use the conjugate sum. The conjugate sum is very good for 0 over 0, but not for other situations, not for infinity over infinity. So this is basically the same method for infinity over infinity, divide out the highest power, or actually highest power, even its best highest power from the denominator. It's even better. So if the highest power is in the denominator, very good. If the highest power is in the numerator, it would still be better to divide out the highest power from denominator. This is an overview. You don't have to copy everything, but just make some notes in your previous notes, perhaps, or anything to remind you how to do things. Infinity minus infinity. That was something that sometimes happened. So in this case, we have to transform it to something else. So in many cases, we also use conjugate sum. In many cases for this, we still use conjugate sum. Of course, don't forget, if you multiply by the conjugate sum, you also need to, if you have a minus b, then you multiply by a plus b and divide by a plus b. Then you simplify the expression, and after that, you will be able again to take the highest power out, because this will generally become infinity over infinity. This kind of thing generally becomes infinity over infinity. So these are, let's say, maybe not very often seen, these limits. However, occasionally they do happen, and then they need this approach, because otherwise it's basically impossible to deal with them. Trigonometric 0 over 0. Of course, we know the limits. We know the one is also a limit, something that approaches one. One is not a constant. 1 is not a constant. If 1 is a constant, then this limit would be equal to 1. If 1 is a constant, then yes. But if it's not a constant, then remember we have this E limit, this special E limit to use. Very special, 1 plus 1 over t to the power t tends to E when t tends to infinity. Never mind positive or negative infinity. So we use this if 1 is not constant. Of course, in most cases, we need to do transformations for this. And then, let me remind you, the equivalent infinitesimals, the final method. The final method. So I remind you, there's no L'Hopital's rule for this unit. No L'Hopital's rule. We will use L'Hopital's rule later, as I said, but before we are allowed to proceed to that, we need to master limits in general, because L'Hopital's rule, I repeat, is based on derivatives. Derivatives are based on limits. We cannot jump ahead. We cannot jump ahead because that would mean some circular reasoning. We would be going in circles. Limits from derivatives, derivatives from limits. So no, not until we have been doing the derivatives. Okay, so that's an overview, just a reminder for you. In fact, if you want, you can take a screenshot of this. You can take a screenshot of this because this overview is not anywhere in the lecture transcripts. Just take a screenshot. I'll give you a few seconds to do that. And then I'm going on to actual practice. Actual practice. So exercises as in exercises. There we go. So how would you propose to deal with this limit? We can do this using trigonometric approach, or we can do this using the traditional, the equivalence approach. Let's try both just for the sake of reminding you. So this would be using the trigonometric approach. I would multiply and divide by the conjugate sum. I would do that. So I have 1 minus cosine square of 4x. I'm simply reminding you from the very beginning how we did this, so that there's no doubt, so that you can actually manage this in the unit test next time. Tangent 6x. Then we understand that the 1 minus cosine square is actually sine square of the same. I have seen too many people making the mistake, forgetting the 4, forgetting everything. Oh, sine square x, and they are happy. Please make sure you do the correct function inside the cosines and sines. X, tangent 6x when x tends to 0. And then a very good, let's say, simplistic approach. But, well, maybe it takes time, but at least it helps if you have problems understanding other approaches. Sine 4x times sine 4x. And I forgot 1 plus cosine 4x, actually, here in the denominator. Here we have x, we have tangent of 6x, and because we understand that this approaches 2, I can take 1/2 in front. 1 divided by 2 taken in front of this. In 1 divided by 2 because this 2, this 1 plus cosine 4x, is in the denominator. Of course, it is in the denominator of the fraction. So I am taking this outside, and now let's remember what we did in this case. So to get sine of 4x, I can divide by 4 and multiply by 4. which means this limit is already 1. So 1/2 times this limit is already 1. Now, for sine 4x, this one, I need 4x, but that means I also have to multiply by 4x. So this is 6x. So one thing I can do, I could multiply or divide by 6x, or I could simply multiply and divide by 6. Because then I have, see, I can say 6x is here, tangent of 6x is here. So these two taken together is 1 again. And then I have, what do we have there? Let's see, 4 times 4 and divided by 6. So the remaining number of factors, numerical factors. So we have 4 times 4, 2 times 6. I can divide out 4. Can always be cancelled out, 8 over 6 or 4 over 3. So I leave it to you to decide how to do this. There are other methods as well. Remember, there was one more method, one more way for classical method. Remember that 1 minus cosine alpha equals 2 times sine square of half angle. So this means that 1 minus cosine 4x can be replaced by 2 times sine square of half of 4x, that is of 2x. Let's try. There is a tiny possibility that we can find this limit as it is. So let's see, square root of 9 plus 7 minus 4, square root of 9 minus 3. Oh no, it is 0 over 0. Okay, so this is 0 over 0, which means I need to factorize. I cannot factorize. Remember what happened in these cases. Remember what happened in these cases. We multiply and we divide by the conjugate sum. So limit when x tends to 3, square root x squared plus 7 minus 4, square root of x plus 6 minus 6. Don't forget parentheses. If you don't use parentheses, you in many cases get things wrong in the end. So to get rid of this radical, I multiply by its conjugate sum. So plus 4 instead of this, and I divide again by the same conjugate sum, plus 4, careful with the radical. That will take care of the first thing. Let's use a different color, perhaps. Different, come on. What's happening? Okay. So I will be taking these together, and this will remain. Nothing happens with that one. Now I am taking care of the other. I need to write the conjugate sum for this other expression, the other radical, x plus 6 plus 6 root x plus 6 plus 6, because I need to eliminate that radical too, because that also creates a 0. So that will be okay. These taken together, and this will remain as it is. It's not a bad thing that it remains as it is, because when we put in the x value 3, it will not be equal to 0. We will be able to compute the value of 3. expression. That's why we never open the parentheses where it is unnecessary, only where it is extremely necessary for the sake of the limit. So now we will see x squared plus 7 without radical minus 4 squared, that's 16, times the radical x plus 6 minus 6, divided by, now the yellow part, x plus 6 without radical now, and minus 36.
Excuse me, miss.
Yeah, it had, yeah, I know, it had to be 3. I just noticed. I was writing and I figured out that it's wrong. So here we need 3, and here we need 3, and here we need 3. I don't know if I say, because x plus 6, of course, yes. I'm sorry. I will just correct it with yellow so that you see. I correct this. I correct this. I correct this. And yes.
I think it's x, not 3.
Oh, yes. Yeah, right. Even worse. Okay, sorry. Okay, I'm correcting some more. Get rid of 3, get rid of 3, get rid of 3. Why did I want to put x? Well, why did I want to put 3? I know why. Okay, going back to 10. So this is x, this is x, this is x. And so this is x squared when we open the parentheses. And yes, of course, we multiply by the remaining conjugate sum of the numerator. Yes, right. Okay, square root x squared plus 7 plus 4. And so we have, okay, now I write the limit, and x tends to 3, x squared minus 9 times square root x plus 6 minus x divided by, now we see it's rather unpleasant, minus x squared plus x plus 6 times radical x squared plus 7 plus 4, rather messy as we can see. But right now we can already, there was a plus. This was a plus. What am I doing there? This is a plus. Okay. At this point, in the non-zero limits, perhaps we should already try to put the 3 in the limits that are definitely not equal to 0. Okay. Oh, now it's much better. All right. I am now putting x is 3 in this limit because it's not 0. I'm putting x is 3 there and x is 3 there because these limits are not 0, which means I can take them out. So it will be square root of 9 plus 3, and this will be square root of 9 plus 7, 16, plus 4. I take it before the limit. And now inside the limit, what remains is, x squared minus 9, I can factorize it easily, x plus 3, x minus 3, and this will be the bad, dangerous factor. In the denominator, I don't like this minus, so what I'm going to do is I'm going to take this minus outside now. I don't like this minus, so I'm taking the minus outside in front of everything. So inside the limit, I have now x squared minus x minus 6 because I'm taking the limit out. And then I can factorize this, of course. So here we have minus, that's this minus. We have 3 plus 3, that's 6. And here we have 4 plus 4, that's 8. Limit when x tends to 3, x plus 3, x minus 3. And here we have x minus 3 times x plus 2. I'm reminding you that if you see x minus 3 as the zero factor in one of the polynomials, for example, in the numerator, then you can be very sure that the same zero factor will show up in the denominator as well, if that makes it easier for you to factorize. Now we can cancel out the zero factors. So we have minus 6, 8, and this is 3 plus 3, 6, and 3 plus 2 is 5. So we can see that sum simplifying is possible, 2 and 3. So we have minus 9 over 10. This is a very complicated limit. Not complicated as a limit, but complicated from algebra viewpoint. Because what has to be done has to be done. Multiply and divide by the conjugate sums. But the algebra part, you see, combining them correctly, then figuring out how to factorize these things. Not to mention my very silly mistake with the x thing. Getting 3, getting 6, getting whatever instead of x, although I had to put just x in there. In principle, I will not give you a limit this complicated in the test, definitely no. What made it especially complicated was that it features squares. The problem with this limit is not so much that it has two radical expressions, one in the numerator and the other in the denominator. But what matters is also that it has squares involved. You see, we have squares involved, and when we find the conjugate sum and multiply by the conjugate sum, another square shows up. So that's the problem, because it takes extra work. So I can promise you that I will not give you anything this difficult for the test, because at this moment I am not testing algebra as much as testing limits, of course. Okay, move on. This is very clearly a limit about equivalence, because as you see, 1 plus 4x inside the logarithm. We don't have a logarithm special formula. So what we see is, of course, sine of t is equivalent to t, and ln of 1 plus t, we remember, is also equivalent to t when t tends to 0. So I can say limit when x tends to 0 of 2x, which is t in the sine case, divided by 4x, which is the t in the logarithm case. So this limit is 1/2. Even though at the beginning it looks rather complicated, so logarithm of 1 plus t is something that is worth remembering. It's worth remembering for the sake of equivalence. This one looks horrible, but just notice, if x tends to infinity, x squared divided by x squared is 1. So in principle, we see that this is the indeterminate form 1 to the power infinity, because we understand that this actually tends to 1. So what is unusual? Unusual is that we see the squares. But it shouldn't be a big problem, because in the end, if you remember, for the E limit, in the end, we basically evaluate a rational expression, a fraction, an algebraic fraction. So what we do here is, evidently, we need to do 1 plus 1 over t to the power t. We would be very happy to do this. when t tends to infinity. So first of all, let's do x squared minus 1 divided by x squared plus 2. Let's change it to this. But to do that, we need to understand what 1 over t is. So we need to split it. Remember what we did. To get 1, evidently I would need x squared plus 2 divided by x squared plus 2 would be 1. But of course, we also need to take care of the correct number, x squared minus 1. To get the correct number, I have to write minus 3. So in fact, I effectively split minus 1 into plus 2 and minus 3. Plus 2 because it will be the same as in the denominator. It would be the same as in the denominator. It would be this. So it would be 1. And then the rest is minus 3 over the same. Minus 3 over the same. So in this case, I would say, so now let us do again 1 over t is minus 3 over x squared plus 2. Please note the minus must be included because because we have a plus in the formula and we have a minus there. So this means the minus must be included in 1 over t. And of course, we see that if x tends to infinity, then t also tends to infinity, although it's negative infinity, but it's still the same. It tends to infinity. In our case, it doesn't matter, positive or negative. In this limit, in this particular limit, it does not. And so now I can write this is the limit of 1 plus 1 over t. Now, that is, this is now fully replaced by 1 plus 1 over t. And now in the numerator, remember, we needed t to make e. But then to eliminate this, we need to multiply by 1 over t and multiply by the correct exponent. Then the exponent is, in fact, what it was at the beginning, as it should be. It should be. We must not change the value of the expression. What we do is we manipulate it, we stretch it, we split it, we transform it. However, the value must not change. So if we do something extra, multiply by something extra, we must divide by that something extra. So here I put t, but to, let's say, to eliminate it, to balance things, I multiply by 1 over t. So to taken together, this is 1. So the actual exponent will not change. Now, the next step was, remember that the limit of this is e. So in fact, I now have the limit when x tends to infinity of e to the power 1 over t times x squared plus 1. 1 over t is this. This is 1 over t. So I'm writing minus 3 divided by x squared plus 2. That's 1 over t times x squared plus 1. So I multiply by x squared plus 1. And now, if necessary, I can do the limit separately. I can again do the limit when x tends to infinity of minus 3x squared minus 3 divided by x squared plus 2. If you don't already recognize what the value of this is, remember dividing out the highest power of infinity. Dividing out the highest power is infinity. So minus 3x squared divided by x squared is minus 3. Minus 3, don't forget to divide it out of the constant. X squared divided by x squared is 1. 2 also divided by x squared. So this limit is minus 3 minus 0 divided by 1 plus 0. So this limit is minus 3. So now we see that this is e to the power minus 3. Or you can write it 1 over e cubed. So this particular limit involved, as an example for you, involved everything. That is, the need to transform the base, the parentheses, the need to transform things. Then the reminder that a minus must be included in 1 over t. That's another thing that might happen in this kind of limit. Then the way we set up the exponent, and then of course the fact that we take e and then we may need to find the limit of the exponent separately, simply not to crowd things here, to make things simpler, do it on the side. So basically the main idea is, of course, this is the main idea, but some tricks or catches. One catch might be that, first of all, we need to transform the base, we need to transform the parentheses. Secondly, another catch, we must make sure we have the sign correct. Sometimes it will be correct already. And then, of course, the third catch is we have to be very careful when evaluating the limit in the exponent. All right, so this kind of thing, I will simply do a very quick reminder of some things. Because we have a test, I am dragging this out a little bit, sorry, but for that, during the test lecture, you don't have any other lecture. So in this case, z tends to 0. Careful, okay. Careful about this. Z tends to 0. This means I can still see this approaches 1 and this approaches infinity because we have 2 divided by 0, that's infinity. We still have 1 to the power infinity type. And that means we can take, evidently, 1 over t, we replace minus 3z by 1 over t. When z tends to 0, evidently t will tend to infinity. That's important. And now we see, all right, limit when z tends to 0. And you may want to write as a reminder, so that means t tends to infinity in our notation. So we have 1 plus 1 over t now, because I took minus and all, everything together, I took and replaced it by 1 over t. Then we do the standard trick, t in the exponent, 1 over t in the exponent. And finally, the exponent as it is, 2 plus z divided by z. Sorry. Okay, now we have e. And so now, okay, we have the limit e to the power, when z tends to 0, yes. Now 1 over t was actually this, so it's minus 3z, that's 1 over t, is this part, times 2 plus z divided by z. So now let us see what's happening here. There will be no need to rewrite it separately because now z tends to 0. So what we have is minus 3z times 2 plus z divided by z. These cancel out. Z tends to 0. So we see that it's e to the power minus 6. E to the power minus 6. Or 1 divided by e to the 6th power. Like this, so having to be a little bit careful because in this case we have to remember that z tends to 0. So when we are considering the exponent altogether, this expression altogether, remember that z tends to 0, which means, yes, it is already taken out as a separate factor in this case. So in principle, the first thing to do is always look at the limit very carefully. See, for example, where does the variable tend? What value does the variable approach? Then try to put that value in. Have a look at which kind of indeterminate form you have, how to approach this. In this case, very carefully, you should know that in this case, x divided by 3x, the base actually tends to 1/3. The limit of this is not 1. It's not 1. It's 1/3 to the power x. It's not 1 to the power x. So this is not an indeterminate form. When x tends to positive infinity, this actually tends to 0. So be very careful. Sometimes there might be a catch not a catch or a trick, but it's just note what is in there. So pay attention to what you see. And I guess this is the last one. This is very definitely to finally remind you one last time. Okay. To remind you one last time of the equivalence thing. Remember that we had something very similar, only we actually had this in terms of logarithm. So remember that, okay, I have to do this. 1 plus t to the power, in this case, it will be 1/2 square root, is equivalent to 1/2 of t. And in this case, t is x times sine x. Minus 1, sorry, there was -1, forgot that. So this means we have limit when x tends to 0 of 1/2 of x sine x divided by x squared. Now this is very easy to do. See, x and the square disappears. Sine x over x is 1. So we have 1/2 times 1, and this limit is 1/2. In fact, very, very simple. Again, if you use equivalence. If you don't, then it's very, very complicated. Then you would need to use, yes, you could use the conjugate sum and then manipulate. It would be possible. But why do that if you can have a very simple approach? Now, this is it. A reminder to everybody that in the unit test, no L'Hopital's rule, no differentiation, only standard classical methods. Also, a reminder that the homework is posted, but it's not for Friday. The homework is for next week, or Monday evening. I simply forgot to post it earlier, that's my fault. However, for the sake of practice, you may want to at least do parts of it for Friday, and remember that homework is basically more difficult than the unit test tends to be, so actually that would be a very good practice for you. All right, I will see some of you for elementary mathematics on Friday for the unit test on limits. And after that, remember, Saturday, our Monday lesson was moved to Saturday the 8th. But on Friday, first of all, we'll write this test.